So, folks, it's our pleasure today to have Professor Guru Parulkar from Stanford speaking to us today. So, Guru is basically, he's worked in industry, in startups, as an NSF program director, as well as academia. So, he's essentially been there, done that as far as anything relating to networking goes. So we're really fortunate to have him talk about essentially so-called software-defined networks, which is a new approach to networking. Please welcome Guru Parulkar.
Thank you, Srinivas. Appreciate it, and thank you all for inviting me to tell you about this software-defined networking, something we have been doing for last 5 years or so, and quite excited about it. And so it's a pleasure to have this opportunity to share with you. I have not done this kind of a WebEx talk before. It's kind of I have done some WebEx meetings. Doing a talk is unusual. So in case my mannerism or if I'm not doing something right, feel free to interrupt me and let me know how I can make it more useful to you. Okay. This work is funded by a group of 12 companies as well as National Science Foundation as well. Okay. So my remote control is not working. Uh-oh, I thought we checked it out. Okay, so let me start with a quote that appeared maybe a couple of weeks ago. It says, SDN, your next network, and SDN has the potential to bring new levels of automation and efficiency to networks. And this was in October, October 3rd, 2012. If you look at Google or anywhere else, there are lots of press releases or articles that are stating SDN is the new approach, a new paradigm, a new revolution in networking, and so on and so forth. Some of this is a lot of hype, as it happens with every technology or everything new that happens. So I want to warn you that look at some of these articles with a grain of salt. On one hand, we are very happy that there is some excitement, there is some momentum. On the other hand, as you know, once the technology is really started, the press and the media people create too much excitement about it. So just be careful how you read some of these articles. What I want to do in next maybe 40-45 minutes is to give you some insight in terms of why people think SDN is a new paradigm or new approach to networking that is likely to have a big impact. I want you to again remind you that we are at the beginning of networking. We still have a long ways to go, but I want to share some insight why people are saying what they are saying. Okay, so here is my executive summary. These are some of the important takeaways. So SDN is emerging as the new paradigm of networking. Industry is embracing it, which is very good. Sometimes they're doing it much faster than you would expect. But at the same time, we still have some ways to go. The second point I want to emphasize is SDN is not just a feature or a new, in terms of, something like you think about yet another protocol or a particular feature. We think of SDN as a new way of thinking in terms of the abstractions for SDN, the programming model for networking, as well as what kind it enables. Automated troubleshooting is one example of the capability that is enabled by SDN, and I try to give you a little bit of insight into why that is the case. The third message I would like to communicate is SDN's value proposition to network owners, to give you some idea why networking owners like SDN, they are wanting to use SDN. Okay. End of the day, it comes down to faster innovation, virtualization, customization, simpler hardware, and so on. And then all of this leads to reduced CapEx, OpEx, and increased revenue. So this is a very pragmatic way of thinking about why SDN. Finally, I want to use last whatever 5 minutes to give you a little bit of a advertisement or a little bit of insight about a new research center that is a joint center between Stanford and Berkeley on something called, we call it Open Networking Research Center, which is exclusively focused on OpenFlow and software-defined network. So before I go to the next slide, are you able to hear me? Are you able to see everything? Is it okay?
Yes, everything is pretty good. Thanks.
Okay, so let me start with this SDN as a new paradigm of networking. Start with what the problem is, what it is, and why it has that potential. So let me start with the problem with the internet infrastructure. What is the problem that SDN is trying to solve? Now, if you look at internet, you can divide it into two parts. The services part that is provided by Twitter and Facebook and so on, and then there's the infrastructure piece. So the infrastructure piece is what you can think of as plumbing of the internet. Now that plumbing of the internet is built using boxes that we typically call switches, routers. Sometimes there are different types of appliances that make up that particular infrastructure or that particular box. Now, if you look inside the box, what you will typically see is, in simple terms, there are these three layers. There is the highest layer is kind of this, or the lowest level is specialized packet forwarding. Then on top of that, you have something called router operating system. If you're familiar with Cisco, that is iOS, June OS, and so on. And then there are a set of features. Why does it get, okay. So the features or applications, control and management applications are like routing, network management, mobility management, access control, VPN. The list goes on and on. So what is wrong about this particular thing is, over the last 20 years, these boxes have become more and more complex, and these boxes have become kind of vertically integrated. So if you look at today, maybe a typical box has 50 million lines of source code. There are over 6,000 RFCs. Not every box is supporting every RFC, but they end up supporting several thousand RFCs. Hardware is kind of billions of gates, bloated, power hungry. But more importantly, these boxes have become more vertically integrated, closed, proprietary, and not suitable for experimental ideas. I know some of you are graduate students, so now imagine if you are a graduate student, you come up with some new idea, new way of doing routing, new way of doing access control, or something along those lines. It becomes too difficult for graduate students to be able to try out their ideas with real boxes and in real networks. And without doing that, it becomes too difficult to have the impact that we are looking for. So the bottom line is, this particular way of building network infrastructure is not good for network owners, it is not good for network users, and obviously it's not good for the researchers as well. If you're a network owner, like as an enterprise like Stanford University or any enterprise, or if you're AT&T, what happens is you get this particular box and you build your network using these closed proprietary boxes. You have few knobs that you can turn, but otherwise you are not able to customize, you are not able to do something on top of your own network because they are closed, proprietary, and difficult to program. So that is one problem. The second problem is a little bit more architectural and more embedded into the architecture itself. And so let me go back to our router, a simplistic router. What happens is, everything in the network architecture or internet architecture done in a very distributed fashion. That means is that every functionality that we want to implement, it gets implemented in a very distributed fashion. So what that means is that you have, if you are, for example, wanting to do routing, you will have a set of functionality that is involved in synchronizing and creating state for the routing or about the network. And then on top of that, you see a little red box, and that is the box that is in the shortest path routing algorithm, which is relatively very, very small, and lot of complexity is spent on synchronizing and creating the state consistent in a distributed fashion. And what ends up happening is every time you want to implement a new feature, you have to first come up with a set of protocol or a protocol that is going to create this consistency among distributed routers, and then whatever logic you want to implement, you are implementing on top of it, and that is a small logic. So what that means is that every time every time you want to implement a new functionality, it is relatively complex, and what that means is that it is not good for even the network vendors. Okay, so if I'm a Cisco or a Juniper and if I want to bring a new capability to the marketplace, I end up implementing this distributed algorithm every time, and then the particular feature I want to implement is relatively small part of what I want to do. Okay, so there are other descriptions of this problem that are used in the industry, and that is in our current way of doing networking, every control and management, we do it on a device-by-device basis. So I'm sure you heard about something called CLI, and using CLI, you are trying to configure every individual device. You don't have a view of the network as a whole. Another thing is that the network is to large infrastructure. There are a number of service providers now wanting to build cloud infrastructure, and they are able to provision and control virtual machines on servers much more easily and using a interface. But hello?
Right. I can hear you.
Are you, is this okay?
Yep. Yeah, that's fine.
Okay, so people who are building this cloud infrastructure, they are able to instantiate VMs, they are able to provision VMs much more easily, but they are not able to provision network quite that easily, and people are observing that networking has become a long pole. Every time you want to provision a new service, networking is a bigger problem. Okay, so these are other descriptions of the problem that people are experiencing. Okay. So now let me, in one slide or two slides, try to tell you what is software-defined networking is. So one point I want to make is software-defined network is nothing radically different in some sense. It combines ideas that have been around in the research community for a long time. Okay, it is just maybe the timing is right, or only 2 or 3 ideas that combining seem to have the kind of effect that we are looking for. So the first idea that we try to bring is the separation of data and control plane. So all this sophisticated logic that is embedded into the router or a switch, we try to lift all that intelligence out of the box, and that is part of now the software and the control plane that is divided between the network operating system and some of these applications that you see on the top. Okay, so that is the first thing we try to do, and again, this is an idea that has been around for a long time. It is just that it makes a lot of sense now than maybe it did before. Another thing we are trying to do as part of SDN is to provide a vendor agnostic protocol between this network control plane and the forwarding elements. So the forwarding elements are relatively simple, and now there is a vendor agnostic protocol between the control plane and these forwarding elements, and this this interface can be layer independent. You can be layer 1, layer 2, layer 3, any one of these layered forwarding devices you can control using this protocol, and that is the protocol we call OpenFlow in this particular case. And then the network operating system, the role of the network operating system is to talk to all of these distributed devices that are spread around the network, and then build what we call network map. So the network operating system is talking to these devices, and at one logically central place, it is building a map of the network. Okay, and that is what is shown there. Once you have that network map, then building these applications that are shown there, like routing, traffic engineering, mobility management, those things become very, very easy. The reason being that these applications do not have to worry about the distributed nature of the network. these applications that are shown there, routing, traffic engineering, mobility management, they are operating on the network map. The network map is something local. It can be in, you can think of it as a data structure in the memory, or it is in a local database. And when you want to do traffic engineering or routing, you are essentially manipulating this data structure or this particular network map that is sitting there. Assuming you can do that, then writing these applications become very, very easy. I mean, undergraduates and graduate students are able to write routing, traffic engineering, mobility management kinds of applications in few weeks or even less. Being able to do it, writing a small piece of code that can be 100 lines of code, a few hundred lines of code, and that is kind of the power of software-defined networking, that you are to build these applications much more easily and very, very quickly. Okay, and then of course the thinking is there will be a well-defined open API that allows people to write these applications. So these applications can come from vendors, these applications can come from third parties, or if I'm a network owner, write applications to manage my network better or control my network better. Okay, so that is kind of in one slide what software-defined networking is. There is one more abstraction that we add that has to do with virtualization. As you can imagine, virtualization has been a very important construct in computer science in general. It has become very important in the server side of things as well. So we try to introduce the concept of virtualization even in networking. And the way to think about it, rather than these control programs directly operating on the network map, the physical network map that may be too complex, by introducing a concept of the virtualization, you can even present an abstract model of the network to the application. So you're trying to make it even easier for people to write applications. So you don't have to worry about all the complexity of the physical network map. You can have a much simpler network map that is presented to you, and you can write your application for that. Or you can create multiple virtual networks and give these virtual networks to different applications and let them manage those virtual networks. So essentially at the end of the day, this is all software-defined networking is all about. So let me take a little break and ask you, am I making sense? Are you able to follow me so far?
I think so, yeah. Any other questions?
Because I think this is the gist of software-defined networking. Now, I will tell you a lot more details, how it is used, what kinds of things people have built on top of it, why it is attractive to industry. But these two slides essentially summarize what SDN is all about. Okay, so I'm able to communicate, right? You are following it, right?
I think we have, yes.
Okay, good. Okay, so let me move on. So if you remember, the first thing I said is, if you do things differently, then we will be able to do more research, we will be able to do innovation. So the question that comes to mind is, okay, we have been working on SDN for 4 or 5 years. Have we enabled any new innovation? Have we enabled more research? So let me tell you something from 2 years ago now. 2 years ago, we were building, part of this Genie program that you may be aware of. This is national infrastructure that NSF is funding to build, and as part of that we built OpenFlow networks in 8 or 10 universities, and those universities are listed there, including BBN, and then we interconnected these OpenFlow networks using 2 OpenFlow enabled backbone networks. I'm sure you know Internet 2 and NLR. So we deployed these OpenFlow enabled backbone networks in Internet 2 and NLR. And so 2 years ago at Genie Engineering Conference, we had this nationwide footprint. Now this footprint is relatively small, but still you can imagine for research and experimentation, large footprint, which is going coast to coast, 2 backbone networks and 10 or 12 places that are interconnected. So on this particular infrastructure, we created the following model. So at the lowest level is the physical infrastructure that I showed you before. Then on top of that, we built something called FlowWizer. The FlowWizer is able to slice the physical network and create the slices of the OpenFlow network and give it to different researchers. Okay. and then these researchers get a slice of the network, and for that slice they can run their own network operating system, and then within that network operating system they can write their own application, control and manage their network. And so there were a number of slices that were run on top of this Genie infrastructure, and then during this Genie engineering conference, we and our collaborators demonstrated a number of interesting applications, or you can think about research application in order to demonstrate some new capability. Okay.
Whose infrastructure is the data plane in that example?
I'm sorry?
Whose infrastructure is the actual data plane in that example?
Oh, so this is, as I mentioned, that there were OpenFlow networks that were deployed on 8 or 10 campuses.
Right, but who's the other side of that OpenFlow connection? Is it like an HP ProCurve, or is it something else? Like, who's actually implementing the data plane layer?
Yeah, okay. So they were, at the time, this is, I'm talking about 2 years ago, they were mostly HP and NEC switches at the time.
Okay.
Okay, and they were all HP NEC switches that were OpenFlow enabled at the time. Now there are almost every vendor has an OpenFlow enabled switch, but at that time they were HP and NEC. Okay.
Which version are you actually seeing that that people are running right now? Is it still version 1, or is it 103 or 102?
Oh, okay. I guess most of the people still run 1.0 OpenFlow version. Now there are starting to be 1.1, 1.2 reference implementations that are coming out. I only know of one vendor that has a 1.3 implementation, but it is not, I mean, I don't think it is available for distribution yet.
Thanks.
Okay. Good. So I guess you are way ahead of me. Okay, good. That, you know, you have with that. Okay. So here is a list of different kinds of research that was demonstrated on that infrastructure, and then later on in other contexts as well. And you can see there is a whole bunch of it. And it is safe to say that this is the type of networking research on a nationwide infrastructure that was something has not been done before or has not been possible before, and something that is enabled by something like SDN. As I mentioned, that was from 2 years ago. Since then, there are maybe over 200 deployments around the world of OpenFlow-based infrastructure, and people are doing all kinds of things. The number is much larger than 200 because after 200 we stopped counting, and we couldn't keep track of the deployment. I will not have time to go through some of these demonstrations or some of the interesting stuff that we have done on top of OpenFlow and SDN, but if you write down this particular URL, you can go and visit, and there are a number of videos that kind of highlight the power of SDN and the kind of capabilities that our graduate students have demonstrated on top of SDN infrastructure. So something to look into when you get a chance. I want to briefly tell you about the kinds of things that we did at Stanford and Berkeley. It started with a project called Ethane, and then we did some specification, we did reference implementations, we built tools, network operating systems, virtualization software, Genie software suite, and then we did a number of deployments. Some of them we did it ourselves. In other cases, we helped the deployment, and in some more cases, we essentially provided email support and kind of online help. And we also did a number of demonstrations that have been well received in order to demonstrate the potential of SDN. Okay, so this is the kind of work we were doing until maybe say a year or so ago. I will tell you about what we are doing now after a few slides. Okay, so this is kind of what was going on maybe a year or so ago. But before I go into the kind of research we are doing now, I want to take a couple of minutes to tell you that this is not anymore just a research project happening at Stanford and Berkeley, and people, it's not just for demonstrating some interesting research. There is all parts of networking industry now that is embracing OpenFlow SDN, and I want to quickly give you a feel for it, and don't, this is the university talks, I don't want to spend too much time about it on this particular part, but I want to give you a feeling that industry is really now engaged, And if you look at the list of companies that are involved, they come from all parts of networking industry. There are some companies that build some of the largest networks like Yahoo or Google, Verizon, Deutsche Telekom, NTT Communications, and then there are some companies that build very large, I mean, they are vendors that build networking products. Then there are some chip companies, there are software companies, and so all these 70+ companies that have joined something called Open Networking Foundation to standardize OpenFlow and promote SDN, that is coming from a very large part of the industry, or all parts of the industry. But it's not that people have just joined a standards organization. You can see that there are a number of companies now that are announcing OpenFlow and SDN products. Almost every day or every week, you will see a number of announcements from a number of companies about SDN products, solutions, strategies, and so on. We also host an event called Open Networking Summit. We had an event in April 2012 where there are 20+ companies that demonstrated OpenFlow SDN-based products, technologies, solutions as well, and it was extremely well received at the time. Okay, so basically, I guess at this point it is safe to say, it is emerged a new way of doing networking, industry is embracing it, and it is happening much, much faster than we imagined. Or even every 6 months we are surprised how quickly the industry is wanting to do this. So what I want to spend next few minutes on is the kind of research we are trying to do now, and I will come back to this again towards end of my talk as well. So to some people, SDN may come across as a feature or just something that they add on to networking, whereas our point of view is SDN really represents a new way of thinking, and it introduces a completely new a way of thinking, reasoning, and of course building networks and so on. And I want to share a little bit of thoughts along those lines. Okay, so if you look at SDN origins, at the time when we started working on OpenFlow and SDN, the thinking was relatively simple. Pictorially it may look very similar, but if you take a minute and look at this, what originally I call network operating system, we still once in a while call it OpenFlow controller, and it was a very, very simplistic thing. It will take the events that are coming from different forwarding elements in terms of when they do a discovery of a link, or when they discover a neighbor, or an endpoint connects, or you're starting to an application. The forwarding elements discover these events and they pass on these events to the network operating system or an OpenFlow controller. The OpenFlow controller used to be very simple. It will take the event and it will pass it on to the application on the top, depending on which application has registered to wanting to see particular type of event. Okay, and so it was very simple, and when you were writing the application, those applications would have to deal with all the events and they will have to figure out what to do with it and so on. So life was relatively complex even in the control plane at the time. Since then, as I mentioned to you, now a lot of our focus is about defining these abstractions. So originally there was no abstraction, there were very primitive stuff. Everything that was happening in the network was getting passed on to this application. Now we think that as we have done in computer science in general, it is very important that as we are building these layers in the control plane, it is important to have these various abstractions, and getting these abstractions right is very important. And the power is in the abstractions, and we can define the right abstraction, then life becomes easier and easier for people that are wanting to write applications, control and management applications on top of that. So all this stuff that I'm talking about in terms of virtualization, defining these abstractions, these are all the new ideas that we are exploring at this point, and that is what we hope is changes the way we think about networking, and we should be thinking about networking in these contexts. And I think the best thing I can do in the short time I have is to give you a pointer to a very, very good talk that Scott Shankar did at one of the Open Networking Summit, and you should write down maybe there is a URL somewhere, or you can do a Google search, where he gave a talk that was titled Future of Networking and Past of Protocol. So this is, if you for a second think about the title, it is very important, because what Scott argued in this particular talk is until recently, until now, networking has been all about protocols. Every time we think about creating a feature, we think about creating a protocol. And then this protocol is what these different endpoints, different routers and switches talk in order to exchange the state, and then they try to implement that particular feature or a capability that we want. So networking has been all about protocols, and then what Scott argues in this particular talk is going forward, if we think about SDN the way we are thinking about it, and we think about SDN in terms of these abstractions, then networking is no more about the protocols, it is more about defining the abstractions and then exploiting these abstractions to do interesting things and offering better and better programming models, and through these abstractions making sure that we are able to reason about networks, we are able to prove something about network, we are able to debug and automate troubleshooting of the network. So this is what I mean by saying that SDN is not just a feature, we are hoping that it will kind of become a new way of thinking about networking. So the question you may ask is, okay, if this is a new way of thinking and through abstraction, how do we benefit? How do SDN abstractions help? So there are two examples. One is network virtualization, and I mean, I think that is very well understood now. Lots of people are using SDN for virtualization, so I will not talk much about that. But there is another thing that is becoming, I mean, we at Stanford as well as at Berkeley doing a lot of work, and that is on automated network troubleshooting. And I think this is a big deal, because in networking so far, troubleshooting, I mean, reasoning about networks, debugging networks, troubleshooting network has been a black art, or it has been very difficult to do, and we believe that with SDN we can make it much easier to do. Again, I will not have time to go into the details of it, but I would highly encourage you to look at this talk by Nick McEwen at the second Open Networking Summit, and the title of the talk was Making SDNs Work. And so here is the claim, or here is the observation, that we use SDN, we use these abstractions, we claim that we will be able to formally verify that our networks are behaving correctly and identify bugs and systematically track down the root cause. Now, if you take a minute and think about it, you will realize that this has been extremely difficult or impossible to do with our current networks. So if, I mean, right now we are in the early stages of this research and we have some early results, but if we are able to do this, and if SDN is able to deliver this particular promise, it will be a big deal, or a major step forward. So let me try to give you a qualitative understanding of why we think this is possible. Okay. So this is another way to look at SDN abstractions that I talked about before. And so the idea is the following, that typically what happens is, if you are a network operator or network programmer, you always begin with an intent. You want, when you are programming the network, you have an intent. What do you want the network to do? The simplest example is shown here, that you may have an intent that A can talk to B, B can talk to C, and A cannot talk to C. This may be a simple intent that you have. Now in SDN context, what you do, you start with that intent, then you kind of translate that from virtualization layer and translate it to the global network view in terms of what A can talk to B means and B can talk to C means in terms of maybe physical devices and the physical addresses. Then you do another translation that you say, okay, if I have these particular intent, I translate them into what we call flow table entries. Those flow table entries get installed in the forwarding elements. Okay, and those are examples of forwarding table entries that you are programming into the devices. Okay, and so the network operating system is responsible for making sure that the flow table entries are installed that reflect intent of the operator. So you can see it is, at some level, it is behaving like how you do programming in general. You start with your intent, you program it, the compiler translates it and maps it into the specific instructions of the computer. Now, as you do with the program translation, even with this particular programming, you may be able to do some checks. You may be able to do some verification. So you may be able to do static checking to see if the policy correctly compiled to the forwarding route. So there may be a tool or a formal way of doing this particular static check. Then the second thing you can do automatic checking is the data path working as specified. So because of these abstractions and the logical centralization of the control plane, and all the state is confined to the forwarding table, you may be able to check through some test packets or otherwise collecting the packet histories and so on. You may be able to verify that the data plane is working correctly. And finally, if you look at the number 3 thing, you may be able to have a debugger. Then when something goes wrong, you are able to again look at the forwarding state, look at what exactly happened in the control plane, and through that you can build automated tools for debugging the problems and being able to do the root cause problem. Now, this is not just qualitative paper design. We have now students who have built various tools in order to build the kind of automated troubleshooting I'm talking about, for static checking, for checking whether the data path is behaving correctly, and then they have built network debuggers for SDN networks to be able to debug and find out the root cause of the problem. We are now in the process of trying out these tools in our own SDN networks, in our own network, and the early results are very promising. And so it gives us a lot of hope that this approach may pan out, and if it really pans out and plays out as we expect, it will represent something pretty significant in the field of networking. Okay, let me take another 30-second break to ask you, are you still following me?
Can you give us an example of some of the tools you're talking about? Like, are you doing things like semantic analysis at the level of something like Frenetic to describe configurations of SDN, or are you actually doing much more lower level analysis of the actual match tables themselves in devices?
Oh yeah. So I think, yeah, so one particular student has built this automatic test packet generation. So you can once you install these flow table entries in the data path, you want to figure out, can you send test packets so you can verify each and every flow table entry or every particular path, and so the first reaction is you will need too many test packets, and as a result it will be too hard. But he has now come up with an idea or way so that by generating a very small number of test packets, you are able to verify all the forwarding entries that you have installed and be able to check whether you don't have certain type of problem. Okay, so that is one type of thing, a tool that has been built.
Is he doing that at the match table level, or is he doing it at the client side of the API level?
I don't know what you mean by client side. So what he's doing is injecting test packets from the edge of the network.
Okay, so he actually is injecting packets. It's not a form of static analysis, right?
No. So there is so the static checking is done by languages like Frenetic, or we have our own ways of doing that kind of static checking. I thought you were talking about the runtime check. So I'm describing the tools that have been. Okay. The third bit is this network debugger. Actually, what they do is they collect all the packet histories. There is a very nice paper about it in Hot SDN. You may want to check it out. What they are doing is, as the packets are going through the network, you collect what they call packet histories, and they can dump all the packet histories into a storage, and then you can write a query language. There is a query language using which you can query what exactly happened, and so you can specify invariants. So you can specify invariants like packets from A should not be able to reach B, and if there is any packet reaching from A to B, then you can find out that in the packet history, and then you can go and trace which packets were able to go from A to B and what are the flow table entries they hit, and as a result you should be able to find out which flow table entry allow the packet to go from A to B. Or you can have an invariant such as there should be no loop in the network. That means any packet should not go to the same port twice, and whenever that invariant is kind of invalidated, you will get an alarm and you will know which flow table entry led to the loop in the network. Okay, so these are the kinds of tools. The packet history is like a platform, and then on that packet history, like the platform, he has built now half a dozen applications for doing network debugging.
Okay.
Okay. Anything else? Am I still making sense? Okay. So let me move on then. So the question you may ask is, okay, this is good. I mean, I gave you some idea about the kind of research we are trying to do and how SDN abstractions and are enabling certain kinds of capabilities that we haven't seen before. I want to spend a little bit of time on why the industry cares. Okay, so I think here is chart that I'm using from Stu LB, who gave a talk at Open Networking Summit. It may seem like a complicated chart, and because I'm not able to point to things, let me see. Are you able to see my pointer?
Yes, yeah.
Okay. So if you
So
look
you can use your mouse pointer.
I'm sorry?
You can use your mouse pointer.
Oh, so this point, okay. So if you look at this particular line, it is what is telling you is how the service provider revenues are growing over the last several years. And we all know the service provider revenues have been growing. Okay. What this is, the exponential curve that is showing you is the traffic growth in the network, and because of that exponential traffic growth, because of video and mobile devices and all of that, what it is trying to show you is the cost is growing fast. So this is what they expect the cost to grow if nothing is done about it. And so you can see if your revenue is growing slowly, right, if the revenue is growing slowly and your costs are likely to grow exponentially, you are going to get into trouble. I mean, you don't need an MBA to understand that, right? So what Stu LB argued is that because of OpenFlow and SDN, what he's saying is that he can reduce the cost because he does not need to buy very complicated boxes. He can buy very simple forwarding elements that do not have all the complexity that current boxes have. So what that means is that the boxes become simpler, much cheaper, and you can buy them with minimal margins, and you can even buy them from, white boxes or from ODM. So that can bring the cost of the capital equipment down. And then the second thing he's saying is that because of SDN, if I'm able to create new services much more quickly, that means I can create revenue generating services quickly. That means my revenue will grow faster, cost is growing slower, and so again, that is very, very attractive to a service provider. So let me give you an example of our own experience in terms of why we think service providers can benefit from SDN. So if you talk to any service providers today, before they are getting into the cloud infrastructure, the two services that the money-making services for service providers are VPN services and traffic engineering services. Now, if you ask how do vendors today implement VPN services and traffic engineering services, I suppose some of you may know they implement using something called MPLS. That is kind of the most recent. They used to do it using ATM, and before that they used to do it using frame relay, but now they're doing this using MPLS. Now if you look at how MPLS is implemented, as I mentioned to you earlier, the way it is implemented is that there are half a dozen protocols such as LDP, IBGP, MPBGP, RSVP, OSPF. All these protocols have been modified in order to support VPNs and traffic engineering with MPLS. And then these protocols are implemented the way I am here, in the same way, distributed fashion that we talked about earlier. It turns out that MPLS is at least 12 or 15 years old, and it turns out there are only 2 or 3 companies that can claim that they know how to make MPLS work at some scale and so on. Right, so it is kind of interesting and revealing that why it makes it so difficult. So again, it points to vendors find it hard to develop solutions using this approach, providers find it too slow, too expensive, and they become too dependent on vendors. So what we did is we asked one of our graduate students to say, hey, if SDN is so cool, can you implement traffic engineering and VPN that service providers implement using SDN approach? So what he did was he, using some emulation, some real hardware, he was able to build very simple hardware emulated network that is shown here. But more importantly, what he did was he took the control plane using network operating system like Knox, and then he implemented all these functions, the routing, discovery, label distribution, and recovery. Now what I want to point out is he implemented these functions. He did not implement all the protocols, because as I was pointing out with Scott's talk and so on, in SDN you don't have to implement all these functions as protocols. You implement these functions as software modules on top of network operating system. So Saurav is the student, Saurav Das, he implemented routing, discovery, label distribution, recovery on top of the Knox operating system, and then on top of that he implemented traffic engineering and VPN, okay, with all the bells and whistles, all the features are there.
So he has a full like LDP stack up there, and he's just essentially getting control plane messages from LDP piped over the API interface. Is that how it works?
No. So you don't implement any of these protocols in SDN. So you want to do label distribution. So you don't even need to do label distribution, because your network operating system can program the labels onto those devices, right, directly.
So okay, so you were moving the need to do LDP. You're just saying what overlay do you want, and you just set that overlay?
Yeah, so you want to either overlay, or you're trying to set up LSPs, right? Different, I mean, with LS for either traffic engineering or for VPNs, you're trying to set up LSPs, and so LSPs are set up by the network operating system, and they are set up in response to the application that you're running on the top, like traffic engineering or VPN. So in response to traffic engineering, if you need to reconfigure the LSP, or if you need to reroute LSPs, that is all, the decision is made by the traffic engineering module, and then the network operating system is implementing that particular rerouting or reconfiguration of LSP.
Okay. What about interacting with other equipment that already does LDP?
Okay, so I think that is the problem that Ericsson tried to solve, that if you have something SDN and externally you are interfacing to LDP, RSVP, then you can build some gateway functions, but that was not the purpose of our work. We just wanted to show that if you wanted to build a pure SDN infrastructure on which you want to support traffic engineering and VPN, what would it take to do it?
Okay.
Okay.
Thanks.
So kind of the key message that Saurav was able to do this in 6 to 9 months. He was able to do it with 4,000 lines of total code that he had to write, compared to if you want to do with MPLS the old-fashioned way. In the open source thing, when we do the counting, it is maybe 600,000 lines of code it takes to be able to implement all these protocols, functions, and traffic engineering and VPN. And so here is one student who was able to do it in 6 to 9 months, and with 4,000 lines of source code, and otherwise it is so hard. I want to mention that obviously Saurav's work is not ready for prime time, it is not production quality and all of that. But it is kind of revealing that one grad student can do it in such, quickly and with such a little effort. And again, that is the power of SDN, because you are not implementing all the distributed functions. Once you get a network map at one location, then you can do lots of interesting things on the top relatively easy.
So if you were to subtract out like the actual distributed functions from that 600,000, what would the comparison then look like?
Actually, in the 600,000 lines of code, it is all those distributed protocols. Now, I cannot tell you that if we strip, because for every protocol, if I have to go and find out how many lines of code is going into this is too difficult to do that exercise. But what I wanted to say is the 6,000 lines of code does not include any platform software. It only includes the protocols that are needed for VPN and traffic engineering. Okay. So then you would think, okay, we just did it in a lab setting, it was not production quality and so on. But then here is a thing that Google announced at April 2012, that now all the inter-data center network is working with OpenFlow and SDN and logically centralized traffic engineering. And here are some of the conclusions from Urs talk that he shared at ONS. Okay, so again, what I'm trying to show is, okay, we make these claims, then we have kind of demonstrated simple prototypes in our lab setting, and now companies that are starting to do it in real networks as well. I think I'm running out of skip some of the stuff in data center space, but the idea is in data centers also, if you want to do multi-tenancy, you want to have all the flexibility and scale. It is turning out to be very difficult to do that with the current legacy way of doing networking. And then on top of that, if you want to have load balancers, firewalls, IDS, in this context, it becomes too hard to do. And so what people are doing in the data center space is they are using this SDN approach, where you can, each tenant can get a virtual network. Virtual network, you can get when the needs of the tenants, you can decide how you want to do load balancing and how do you want to do security and all of that. And this is a very, very active area of work in the industry with SDN, and that's where it is gaining the most traction. There are some early adopters that are already deploying it in their production network, and you can read a lot more about it online as well.
So in the case of the, excuse me, yeah. So in the case of the Google case, so do you think that the Google can handle all of the switches just using the one controller, or they have to use some kind of the distributed controller?
So I think you're right. So I think they, in the phase 0 or phase 1 of what they did, the traffic engineering part was centralized. Some of the other control plane, as I understand, was still kind of distributed, but it was distributed but not within the box. It was lifted out of the box and it was running on some kind of a server.
So in the cases that they mean to consider like the consistency problem between the controllers. So do you have any kind of clear solution to solve this kind of issue? I mean, the consistency problem between the controllers.
What is the problem you're referring to? I'm sorry, I didn't get it.
I mean, I'm talking about some consistency problem between the controllers. So I think that they need to show the natural underlying information. So
are you talking about consistency among multiple controllers if you are running multiple controllers? Okay.
That's right.
I think that's a good question, and these multiple controllers don't have to be, as I said, they don't have to be within the boxes. You can lift them out and you can implement them even on multiple servers that are running on in a tightly coupled environment within a server, within a cluster, for example. And there you can use number of tried distributed system solutions for having multiple servers keep the state information consistent. And that's what, if you're familiar with Nicira and their operating system called network operating system called Onyx, that is what they try to do. And then the kind of scale of network that you can support is extremely large. And I think maybe we can get into it later offline, but it's not as big a deal as you may think to begin with. Okay?
Okay, thank you. Yeah.
Okay, so in enterprise, what is happening is, you might have seen this, that network operators, all of these, and the way they do this is by adding lots of appliances. So if you have anyone from your campus networking environment, they will tell you that there has been a proliferation of these appliances in campus networks or enterprise networks. And what that means is that increased management complexity, because all of this management is device oriented, and for each device type has its own network management. So you end up having people that are become expert in each devices, and then you have its own way of managing it, and it is too difficult. And I mean, it leads to high capex, high opex, and so on, and too much reliance on vendors. So what enterprises are trying to do, this is how they are wanting to use SDN. This is in early stages of exploration. We are building our SDN network using this for the campus network, and so this is not for research now. This is for our campus network, where they are doing this, that they are moving a lot of these appliances in software. So rather than implementing these functionalities using appliances, they are trying to implement these functionalities using software running on top of network operating system. I don't have a lot of hands-on experience, or we don't have results yet whether this experiment will be successful or not, but this is what number of enterprises and universities are trying to do, and we will see how well it works. And another thing that campuses and enterprises are trying to do is the delegation. If you have a central campus network organization, and then you have a number of departments or different functional organizations, you should be able to give them the control of the virtual network. And again, this becomes much easier with virtualization, and then you can have network operating system, and each virtual network can decide what kind of functionality they want to implement on top of their virtual network. So the bottom line is the following, and that is SDN implication.
Excuse me, actually in the previous slide, so in this case, is what any kind of conflict between the policy routing and some access control policy?
Yeah, so I mean, there could be those kinds of conflicts. I don't know if you saw my earlier slide. So when you're doing the virtualization or when you're doing the slicing, you have to give it policies of your access control and so on, and the FlowWiser or your virtualization software is responsible for making sure that you are following those policies, and either a network controller is not stepping on somebody else flow table entries or not doing something to impact another virtual network. So
yeah, I understand about the FlowWiser, but I mean that what if just the two different applications for the one controller has set up the different policies? Then in the cases they need to handle this kind of conflict. But I don't think the FlowWiser can handle this kind of problem.
Oh, so you're saying applications running within a single network operating system, or are running on top of one network operating system?
I mean the two applications running on a single network operating system.
Oh, right, but that is relatively easier to solve, right? Because that is the job of a network operating system, to be able to arbitrate. I mean, that's what typically, that's why it is called operating system, because it is arbitrating access among different applications and making sure that applications are not violating each other's policies or don't create inconsistent state information. So that is, for a single network operating system that is supporting multiple applications, that is a much easier problem to solve than you have multiple virtual networks, making sure that they are not stepping on each other.
Okay, yeah, thank you.
Okay. So I think the larger takeaway I would like you to think is, if SDN is successful and if SDN really takes hold, the net result would be that the network industry will function like a software industry. And if that happens, as you know, in the software industry, the innovation rate is much faster because people can, and you can have default standards. You can have open source will play an important role, and through open source you can do innovation faster, and so on. Okay, so I guess I want to spend just a few more minutes. Is it okay if I spend another 5 minutes? Or?
Absolutely.
Okay, so I want to give you a quick kind of, and you can think of it as an advertisement or some insight into what we are doing next. In the past year, we set up a new research center between Stanford and Berkeley. It's called Open Networking Research Center. This Open Networking Research Center is exclusively focused on OpenFlow and software-defined networking. It has 3 parts to it. There is a research at Berkeley, there is a research at Stanford, and as you can imagine, the research at Stanford and Berkeley that is done with the help of PhD students, postdocs, and so on, which is very classic. But more interesting thing is we set up this independent organization called Open Networking Lab, and the role of the Open Networking Lab is to create open source SDN tools and platforms that we can share with the larger community, and then through that being able to accelerate SDN development and allow research community and education community to build on those SDN tools and platforms and apply SDN to different domains of use, data center, enterprise, service and is kind of the three parts. And within the Open Networking Lab, the idea is to build a core team of 12 to 15 engineers. So these are engineers, not necessarily, not graduate students. These are engineers with experience in the industry and so on, who are familiar with building better quality tools and platforms that can be given to the larger community, for example. On terms of research, broaden and deepen our understanding of SDN, so it becomes the way people think. So this is about, but the important thing is we also care about impact. So we want to help SDN become widely deployed and used in a variety of contexts. And we are hoping that SDN becomes part of every CS major's training and a natural part of the hacker culture. Because if SDN becomes kind of software-based industry, or networking becomes more software-based, then clearly hacker community can play a big role, and we want that. So I think I want to tell you about our research agenda, and so you can think of it, there are three dimensions to our research agenda. There is the abstractions, and so then there are systems that we are trying to build, and then there are these facilities that we are trying to support. So when it comes to abstraction, we are talking about flow space, network map, virtual network, big connector. These are some of the abstractions. These are our first set of thoughts. Who knows whether these are the right abstractions or not, but these are the things that we are interested in exploring. When it comes to systems that embody these abstractions, and we can demonstrate systems around these abstractions, then there's a whole bunch of systems that we are building as well. We are interested in exploring and building, and again, we are building prototypes, and then we are collaborating with the companies, and some of the companies may bring out products in the space. And then we are, of course, interested in understanding how to make SDN more scalable, as well as individual components more scalable, reliable, secure as well. So these are kind of three dimensions along which we are defining our research agenda and what we are trying to do. So I think there is a number of industry partners that we have that we are working with, and this is kind of my last slide. I'm done. Okay, sorry I took a little longer, but hopefully we still have time for Q&A.